Exponential functions. So we've taken a look at linear functions, quadratic functions. Now we're going to take a look at a new type of function, exponential functions. And before we get to that, we want to review our exponent rules. You'll notice that I put the answers to the warm-up there, so you might want to try those questions and make sure that you can get those solutions. Just going over our exponent rules, we know that if we have the same base and we're multiplying, we're going to add our exponents. If we are dividing, again, must be the same base, we are going to subtract our exponents. Anything to the power of 0 is equal to 1. If we have an exponent outside of our brackets, we are going to apply the exponent to all parts of what's inside, even if it's a number. And same idea if it's a fraction, we're still going to apply that exponent to all parts of what's inside. If we have a single base with multiple exponents, we are going to multiply our exponents. And if we have a negative exponent, we are going to flip it to make that a positive exponent on the bottom. If it was on the bottom, flips to the top to become a positive exponent. So keeping those rules in mind, we're going to take a look at graphing some exponential functions. So an exponential function is any function that has the variable as the exponent. So you'll notice for all 6 of these functions, our x is our exponent. So taking a look at coming up with our table of values so we can graph these functions. If we have 2 to the power of 4, we are going to have 2 times 2 times 2 times 2, which means we have 16. 2 to the power of 3 is 8. 2 squared is 4. 2 to the 1 is 2. 2 to the 0 is 1, which we know that is going to be the case for all of these functions. We can fill that one in pretty quickly. If we have an exponent of -1, that means we are going to flip it to make that a positive exponent, so 1 over 2. If we have 2 to the -2, it's going to flip. 1 over 2 squared becomes 1/4. If we have 1 over 2 to the power of 3, it's going to become 1/8. And 2 to the -4 becomes 1 over 2 to the power of 4, which simplifying gives us 1 over 16. Now, if we start the other way and we have 1/2 to the power of 4, means we have 1/2 times 1/2 times 1/2 times 1/2 is going to give us 1/16. 1/2 times 1/2 times 1/2 gives us 1 over 8, 1 over 4, and 1 over 2. Now, if we have 1/2 to the -1, that means we're going to flip that and it becomes 2 over 1, which is just 2. 2 squared over 1 is 4. 3 squared over 1 is 8. And 4 squared over 1 is 16. Following the same patterns, if we have 3 to the power of 4, we're going to have 81. 3 cubed is 27. 3 squared is 9. 3, 1/3, 1/9, 1/27, and 1 over 81. Now 1/3. So we're going to have 1/3 to the power of 4 gives us 1 over 81, 1 over 27, 1 over 9, 1/3, and negative means it's going to flip. So we're going to have 1 over 3 to the -1 flips to 3 over 1 to the 1, then 9, 27, and 81. If we have 4 to the power of 4, that means we're going to get 256. 4 to the power of 3 is 64. 4 squared, 16. 4 to the 1. And again, when we flip, we notice we're going to get 1 over 4, 1 over 16, 1 over 64, and 1 over 256. 1/4 to the power of 4, and you'll notice that our pattern goes in reverse of what we had when we had 4 to the power of x. So 1 over 256, 1 over 64, 1/16, 1/4. When we flip that, we're going to get 4, 16, 64, and 256. So now you're going to want to graph all of these functions. So you may want to stop the recording, graph our functions. I am going to move ahead just to save time and take a look at all of our graphs here. So you can see that I have color-coded mine. So the red one here is y equals 2 to the x in here. The blue one over here is y equals 1/2 to the x. We have the green one here is y to the 3x. Purple, y equals 1 over 3 to the power of x, etc. So we can see that they all have some things in common here. So they have the same y-intercept. They pass through the y-axis at the same spot, which makes sense because anything to the power of 0 is just equal to 1. So we should have that the same here at all times. Now, taking a look at some of the properties of our functions here. So, domain for the following functions, we notice that the domain of each relationship is that x can be any real number. And this is the case for all of our functions. We could sub any value in here. Sorry, that's going to be x equals any real number. So we could sub any value in for x here and come out with a y value. There are no restrictions there. Now, our range on the other case, there are restrictions. Notice that we are never going to have an x value, a y value of 0. So we notice that our range for all of these functions is y such that y is going to be greater than or equal to 0. And as long as it is, y can be any real number. So that is going to be the same for all of our functions here as well. Now, our x-intercept, there isn't one. As we talked about, y can never be equal to 0. It is going to, for the case of y equals 2 to the power of x, when we have our negative exponents, it's going to get closer and closer to 0, but it's always going to be a fraction. If we have our case of y equals 1/2 to the power of x, when we have our positive exponents, it's getting smaller and smaller and smaller, closer to 0, but we'll never get there. So none of our functions are going to have any x-intercept. Our y-intercept is always going to be 1. Again, because if we have an exponent of 0, it's always going to be equal to 1. So you can see that all of our functions have a lot of the same base properties. So the domain's the same, the range is the same, we have no x-intercepts, and we have a common y-intercept as well. Now, we have two different directions that our functions are going. So if as the x value increases, so as x gets bigger, if the y value also increases, this function is called an increasing function. So both variables are increasing at the same time. So an increasing function. Or we also call this, in this type of function, exponential growth. If, as in the case of y equals 1/2 to the x, y equals 1/3 to the x, y equals 1/4 to the x, the x value increases, the y value decreases, then the function is called a decreasing function, or exponential decay. Our answer is getting less and less, or smaller and smaller. Okay, so this is our introduction to exponential functions. Remember, the exponent must be the variable for this to be exponential function, either growth or decay. So you have some questions to practice on your worksheets.